Hello, and welcome to sections 17.1 and 17.4. In this video, we'll be going over example 1 and introducing the concept of mass moment of inertia. So example 1 asks us to find the mass moment of inertia of this upside down ice cream cone thing here. They give us a density, so before we can solve this, we need to talk about mass moment of inertia. So consider I have a bar and I have a mass, so two masses on each one. If I position those masses close to the rotation point and spin it, this will spin much easier than if I spin this one. These both have the same mass. This one is said to have a higher mass moment of inertia, basically the resistance to rotation. So the generic equation for mass moment of inertia is I equal to integral r squared dm, where this is the radius to the mass and this is some infinitesimally small piece of mass. If we model, basically if the thing that we are finding the mass moment of inertia of has a constant density, then we can rewrite this integral r squared rho dv. So this is mass, this is density, and this is volume. So now it becomes more of a geometric problem. If the density is constant, it'll pop out on the outside, so you just basically put the p out here. Sorry, the rho, not the p. The rho will go out here. So that's for any generic shape. For common shapes, such as discs and plates and whatnot, your book defines the mass moment of inertia for a lot of these. So two of the most common ones are a thin circular disc and a thin plate. So we're looking at a thin circular disc because we're going to need it for our example 1, but there's a whole bunch in here that we can use for other stuff later. So this is in the very back of your book. So you'll notice that for a thin circular disc, the mass moment of inertia about the x-axis, so xx, and about the y-axis, yy. And so later on, when we get into, like, I think chapter 21, we'll learn about ixy and iyx, but those are not mass moments of inertia. So xx just means mass moment of inertia about the x-axis. Iyy means mass moment of inertia about the y-axis. Izz is for the z-axis, and then z prime is about the edge of this disc, which can be useful for things like wheels that are rolling on the ground. And so it gives you an equation in terms of mass and the radius of the disc. So let's look at our example. So we have this shape. It has a height of 1 foot, a radius of 1 foot, and a curve defined by y squared equal to x. So this is in the xy axis. Z is coming out of the page. We want to find I, y. So if we imagine this shape, we could, instead of having infinitesimally small pieces of mass, we could have pieces of volume, which would be thin circular discs. So you could think we have a disc here, and I can kind of color in the edge. That's not a very good disc, but we have these discs here, and we could just stack them on top of each other and create, if they're super thin, we could make this shape out of super thin discs. So the equation for that disc, let's go back and write that down real quick. So it is about the y-axis, but the disc is oriented such that y is this one. So it says z here, but it's actually going to be y for our problem because of the way that things are oriented. So we want to pull this IZZ formula. So that is 1/2 m for mass, radius, squared. So that is the mass moment of inertia about the axis, basically the axle of the wheel. All right, so I've rewritten it So this is going to be IY. So if we have a disk, again, we have a disk, and we kind of go out the center of the disk, it'll have a mass moment of inertia. So that's what it will be for that. But I want to find it for this entire shape. So that means I need to probably integrate from 0 to the top of this thing, stacking up my disks. So to do that, we need to turn this into a derivative. So a partial piece of IY, so DIY, 1/2 partial piece of mass, radius squared. So it starts to look like that initial problem, but it's slightly different. So we took the derivative of both sides is what we did. And we're going to work on just the right-hand side for right now. When we get done, we will integrate both sides and we'll be able to find IY. So 1/2. So the mass of this, we noted we could do rho dV. Up here, this is rho. It's constant, so this will become a 5. I can go ahead and do that for you if you want. So it's 5 slug per cubic foot. And then R, well, our radius of our disk is going to be defined in this x direction, so we can just call this x squared. All right. So let's keep cleaning this up. So we have 1/2 times 5 dV x squared. So now we want to take this dV and break it apart. So you can imagine that we now have disks, which are cylinders, and we just want the volume of a cylinder. So that's going to become, so I'll just kind of draw a cylinder over here. It'll have some height in the y, some dy. It'll have some radius in the x. So 1/2 times 5 times, so let's skip that line. I messed that up. All right, let's move our 5 over here. So we'll have 5 halves, and let's break apart dV. So dV will become pi r squared times height. So pi r, again, r is just x. So we're doing pi r squared h is what we're doing here. That's a cylinder. Our r is x, so pi x squared, and our height is dy, because it's a piece of the total height. And then we bring our x squared down from up here. And so now we're ready to integrate this thing. Once we clean it up, we'll clean it up one more time. So we have 5 pi over 2, that's just a number. And then we have x squared, and we have x squared. So we have a total of x to the 4th power dy. And so this is diy. So if I integrate both sides, I will get iy on this side. And I'm going to integrate for y. So I'm going to integrate from 0 to 1, because that was the total height of our ice cream cone here. So we do that. We get that iy is equal to 5 pi over 2, so that part just pops out, it's a constant, and we get x to the 5th over 5 from 1 to 0. Oops, that is an x, not a y. Sorry about that. So we have to make this into a y before we can do anything. So we want to integrate diy. We're going to go from 0 to 1. 5 pi over 2. So we don't want this to be an x. We want this to be a y. So if I come back up here, you can remember that 1x is equal to a y squared. So we can throw a y squared in here. And so now I will get that this is equal to 5 pi over 2 integral 0 to 1 of y to the 8th power dy. All right, and we're almost done now. Iy, 5 pi over 2, y to the 9th over 9, from 1 to 0. Plug that in, you're going to get 1/9. So you get 5 pi over 2 times 9, so 5 pi over 18, which should become 0.8727 slug feet cubed when you are done. All right. Sorry about that. All right, if you have any questions, feel free to send me a message.